So no problem. Okay. So we talk about a lot about a rectangular matrix has a right inverse. How about the consequences for a rectangular matrix has a left inverse? So if an n times n matrix has a left inverse C, of course the dimension should be n times n. Then any linear system Ax equal to P. N. Okay, so for any linear system, base at most one solution. Remember that if a matrix has the right inverse, then any linear system is at least one solution, right? At least one. But now, on the contrary, if a matrix A has left inverse, then we can at most one solution. It means that it's possible no solution. And if it has a solution, then this solution must be unique. Okay? Okay, so we have this one. So if Ax equal to B, or B in R M is inconsistent, then there is no solution. Okay, right? So if the linear system for a B in Rm is inconsistent, then there is no solution. If Ax equal to B for a B in Rm is consistent, right? It's consistent. Then we apply CA, X equal to B. Right? implies that so if the system is consistent, then the solution must be C. Okay, so either there is no solution, or if there is a solution, means that the system is consistent, then the solution must be C times B, except only this. It's possible you will argue that how come you just do this case CAX? You start from here and you can put a C and C here, and you say, oh, there's always a solution. But you got trouble because it's possible this has no solution. So there is no such identity at all. If there's nothing, put C. It's nonsense. Okay? So before you put C here, you have to make sure that it is consistent. Means that there is a solution. But once it has a solution, this solution must be equal. At this moment, you will say, now, what is the sufficient and necessary condition for a rectangular matrix to have a negative? Right? How can I make up such a theorem? So, and M times N matrix. A left inverse. C, which is if and only if the kernel of A is the trivial set. Do I surprise you? Bro, this direction is easy. Now, so U is in the kernel of A, right? You can only say U. So maybe I put X, right? A vector in the kernel of A, it satisfies the homogeneous linear system, right? But we know homogeneous linear system always has a solution. Why? Because zero vector is at least one solution, right? So X is in the kernel. This is which is always this is consistent, right? So the homogeneous linear system is consistent. So by our previous theorem, says that we have at most one solution. And so it says that X is equal to 0 by the previous. So if x is in kernel, then x must be equal to 0. So our conclusion is that kernel of A consists of the 0 vector. Okay, so this is the direction. It's fine. So it's easy, right? This way. The other way. We assume kernel. And we want to construct the left inverse direction. How can we do that? How can we do that? So let me do some mind solve, okay? Because to solve, because we want to solve this is the idea, right? I just said here informally, right? What I'm thinking about this problem. So this is A is m times n, and I want to find a matrix, right? Unknown. I don't know whether it exists or not, right? So this is n times n. So I get n times n. I try to find an X matrix. How can I solve it? By our Gauss-Jordan method. Well, we have to transpose it, right? This is the technique we used before. So we take the transpose. Okay? So we take the transpose. Now we have AT and X. Now the unknown is in this side, right? So we can solve the matrix equation. And this is again identity. Okay, so now I just replace this as X, right? Again. And this is known, right? And this is unknown. And I try to solve it. Okay, now I try to solve it. So it's just solving, as we know, let me address it. So that we know that we are going to the augmented, the generalized augmented matrix is like this one, right? We have done that several times. Okay. Did you? If you don't, please let me know. I should bear you, right? You say no, means that you didn't do the exercise I assigned to you, right? Is that right? Am I correct? So, this is solving the problem. Okay? And so if every column here has figure, because after the operations, right, you end up with Q and something, say C, okay, C. Now you end up with this one. And you have figures, so that somewhere you have a figure here. So how do we make sure that we have the solution? Well, if again, because even though you have a standard, because it's just like let me write this is just that one. Okay. Right. So if 80, if the columns of 80, span the Rn, so this has a solution, or okay, so maybe I try gradually. So so I can write AP xi okay, because that now this is A transpose is n times n, and this is n times n. So I have n columns. The X has n columns, and the identity matrix has n columns too. So each column is a standard unit vector like this one. So that if the columns of A transpose, all right, if the columns of A transpose span Rn, then solution is equal to Ui this. Okay, right? So we will have that, right? And if we have that, so that A transpose, and we have U1, U2 up to UN, and this is equal to U1, U up to UN, and this is identity, and this is A transpose, and we call this is D dimensions. Right. Now I transpose them again, so I have D transpose A equal to identity. And I let this one to be C, and then I get to the definite inverse. This is my plot. Is that okay? My plot is like this one. So this is the thinking. So everything is that depends on what? Depends on the columns of the transpose A should span Rn. And how do we connect this fact to the kernel of A is trivial, right? So I have to do the connection. So this takes 5 minutes break, and then go back. So since kernel A is the singleton, which consists of only 0 vector elements. The only solution of a homogeneous linear system is x equals 0. Okay? So which means that the columns one, which up to 7 are linearly independent. Right? You already know that. Right? So that you have trivial solution because only the columns of A are linearly independent. Okay? So that's the rows, the n rows. Of A transpose P, which is okay. So the transpose of A actually we transpose the column into rows, right? And so the n rows of A P are linearly independent. Right? Then the reduced row echelon form U of A transpose has no zero rows. Because in before, if the reduced row echelon form has zero rows, then it means that the rows of this matrix are linearly dependent. We have a theorem stated that in chapter 1. Okay? Alright, so there's no zero rows. Right? Thus, thus we have n pivots. So each row and each row of U contains a pivot. So each row of U contains. Okay, up to now, it's good for you. You use the knowledge in chapter 1, right? Because we know how to manipulate the dot operations. Okay, so now we are well prepared to go back to our plane here. We are prepared. Now, so we want to solve. Right? We want to solve this equation. Alright, so consider n linear system. AP xi line where di standard univector. So the associated augmented matrix, right? AP and I. By applying the operation, we reduce to U and U I. This is do about the operations, and do that, right? Any problem up to now? This procedure is standard, right? You just do the operations. So that this is the reduced echelon form of the augmented matrix. So that this part, the U is the reduced echelon form of A transpose. And the standard unit vector turns to just some vector UI. Right? Maybe just do the operations. Any questions up here? Now, you know, there is no zero rows, right? Every row has a figure. So this system is consistent, right? Always has a solution. Right? So which is consistent? Okay. Probably I don't use UI. Maybe I change my mind to VI. Because I want to reserve UI later for later use. That's just UI. Okay? So it's consistent. Since there is no zero rows. Alright. Okay, and so we have a solution, right? At least one solution. So we already solved it, right? So there is a solution, and we connect everything together. So we go back, right? Just do the big work, and then I rest here. So now, there is a solution. Such that AP UI equals to UI. We have a solution. Because it's consistent, so that is constant. And so now we now construct our left inverse AP U1 U2 UN U1 Okay, and so we have A, P, P equal to identity, where P is the matrix. Okay, and then I take the transform, and which is the identity. Okay. That's C equal to T transpose is the left inverse of A, and then with that as reflected, right? Any questions? So this time you can review the thinking I was making here. The purpose is here. I want to construct the left inverse. And so I get a transpose. And then I have to solve such a linear system. A linear system here. Okay? So I have to have something to guarantee that this linear system has a solution. And we resort back to the law operations. So again, every time when you want to know some insight, you go back to the reduced echelon form. That is the root, everything about the linear systems. So we find, and we have a solution if it is consistent, right? And how to make sure that it's consistent? One is that there is no zero rows, means that every row has figure. Or if you have zero rows, you have to make sure this here has zero entrances. But that's hard, right? It's hard. It depends on what you get at the beginning of EI. Right? It's hard. So the easiest thing is that if you know U has no zero rows, means that every row has figure, then it is consistent. That is easy. So that how do we know that the reduced echelon form of H transpose has no zero rows? Then how we know if the rows of AT are linearly independent? Okay, and so go back to here, linear independent. So if the rows are linear independent, then the columns A will be linearly independent. And the columns of A is linearly independent because the kernel is zero. It's trivial. And we're done. So everything connected together. But the proof will be the other way, right? This is the thinking. We have the goal and we want to reach the goal, and how can we do? So that is the proof when you plot something. But when you do the formal proof, you have to do it in the other way. Any questions? All right. So you have two good theorems to use, right? Just to identify which matrix has left inverse. So you just look at the kernel, this kernel. You want to check whether a matrix has a right inverse, then you check the column space of the matrix and to see if the column space is equal to its codomain Rn. All right, so now we go forward to we have talked about square matrix, the inverse of square matrix before, right? So let's just review. A square matrix. Okay. Oh, okay. But this and M times M matrix. A. Let's say definition. All right, I don't repeat the definition. It's invertible if there exists an M times M matrix B such that AB equals to BA equals to identity. there exists, and we remark, we have shown before, if an M times M matrix has an inverse then there is only one such inverse. Right? So means that it's unique. Okay, so remark. The inverse of an invertible M times M matrix is both left inverse and the right inverse. So by definition, when we say that maybe I just said so an inverse of an invertible matrix for M times M matrix is both a left inverse and a right inverse of it. Okay? So, so there is a question. So the question is, can we form an M times M matrix? Okay. Is it possible that it's possible that one A C A equal to B, second A B equal to third such as C equal to B. Right? We may ask this question that the square matrix has a left inverse. And also, the square has a right inverse. And so that left inverse and right inverse are not equal. Because the definition is very strong, right? The definition says that a matrix A is invertible if I can find a square matrix serve as the right inverse as well as the left inverse. simultaneously at the same time. That is the definition of invertible matrix. So you have to find a matrix, square matrix, such that this matrix is a right inverse of A and also a left inverse of A. Okay. And we prove that if we have such an inverse, then it is unique, no others. Okay? But we haven't ruled out the possibility here that we have just a left inverse but not a right inverse of A. And the B is just a right inverse but not a left inverse. Okay? And so that C not equal to B. We haven't ruled out this possibility. So we may ask this question. Is that okay? Now, theorem. We'll rule out this possibility. Okay? So, if A and B are M times M matrix, right? Such that B times A equal to the identity. Then A times B is also equal to the identity. What is in A? It says that if B is a left inverse of A, then B is also a right inverse of B. And so by this definition, B is an inverse of A. And so it's unique. So now we over here. Another way is to say if A is a right inverse of B, then A is also a left inverse of B. The other way, you can look at it wrong, right? So C is a left inverse of A, so C must be a right inverse of A, right? By the theorem. And so C is an inverse of A. Secondly, yeah, B is a right inverse of A. So B is also a left inverse of A. And so B is the inverse of A. But inverse of A is unique, so B must be equal to C. So this is impossible. So the question is no. The answer is no, because of the theorem here. And the proof. The proof of this theorem has the essence as in the previous theorem. So let's see how to proceed it. Okay. So we start with here, right? Since CA equal to IE, B is a left inverse of A, right? So we know that this is given, right? So we know B is a left inverse of A. So the kernel of A is just here. So and then the reduced row echelon form. U of A, right? Is M. So NTHU. And then then each column of the reduced row echelon form U of A is a pivot. Why? Because if the co-reduced echelon form, I think you know that before because we have theorem in chapter 1. I think I forgot it. Because you know when we solve a homogeneous linear system. Okay? So now if you have a column without any pivot, then the corresponding variable will become to be free. And you have a non-trivial solution. So the kernel cannot be trivial. We have a lot of experience like this one. So now I think I don't need to say that. Okay. So anyway. Alright, so let's say every column of the reduced echelon form U of A has pivot. Now okay, so first it has a pivot. Alright, and so so to solve and M times M matrix X in AX equals identity. Right? Because we want to find what? We want to find right inverse, right? We have to prove that. So now we solve such a metric equation. Okay? To solve the associated augmented matrix A identity U and say like W. Okay, so this is M times M. This is M times M. Okay, and because that every column has pivot, all right, and you have M columns, so you have M pivot. How many rows do you have? You have M rows, so every row has a pivot, right? So now every row of U is a pivot, so that W is consistent. Consistent, right? So there is a solution. Okay? And well, I can do it more explicit. Every law of U has a pivot, right? And so that every okay. So I do it here. You know, every column has a pivot, and you have m rows, m columns. So that I just said it's much more easier. U is the identity. U must be an identity, right? No other choice. Every column has a pivot. Every row has a pivot. Must be identity. No other choice. It's very strong, right? So I got I. And so that's x equal to w is a solution, right? I.e., we have AW equal to identity. So now I find the right inverse for A. Is that okay? Alright? So I start from a left inverse, because I know B is a left inverse of A. And I find a right inverse. Okay. So now, right? So now I will check AB. Okay, here. So AB, I multiply with identity. And AB, now I is AW. Any questions up here? And by associativity, number. But BA is identity. So it's A, I, W. And this is AW. And AW is I. And I have done. Okay. Complete proof. So the strategy is that with this given condition, I can find a right inverse x here for A, and then I prove that with the help of this x, I prove that B is also a right inverse by using the procedure. So the importance of the theory says that when you consider a square matrix, this is a privilege only for square matrices, not for general rectangular matrix. Okay, it's a privilege. So you have to know it's a square matrix. So if you are given a square matrix A, if you find a right inverse, then this right inverse must be also a left inverse, and then it is the inverse. On the other hand, if you find a left inverse for this A, then you know this left inverse must be a right inverse simultaneously. And so this left inverse is indeed an inverse, and so it's indeed. Okay? So colors. So I have if for a square matrix A, if CA equal to identity and AB equal to identity. So if I have that means then C must be equal to B. Right. So basically we answer our question. So if I have 1 and 2, I and 2 will imply that C equal to B. So that put together this is not true. Okay? So we have so C equal to B. And also corollary for an m times n, so for any square matrix. If AB is equal to AC equal to identity, so if B and C are two right inverse, then B equal to C. I think that is obvious because if B is a right inverse, then B is also a left inverse, and so B is an inverse of A. If C is a right inverse of A, then of course C is also the left inverse of A, and so C is an inverse, but inverse is unique, so it must be equal to C. And I can state another corollary, right? You know what I want to state. If CA equal to CA, your identity, then equals done. So things turns out very easy, right? Wow, I almost done everything in 3.2. Faster than my expectations. Okay, I can finish my job before 12 o'clock. That's great. Okay, so now that's theorem. Actually, I think we have mentioned that before. And okay, if 2 n times n matrix A and B are invertible, then A times B is also invertible. I think we proved that before, but I'll say that again. And the inverse of A is B inverse times A inverse. So I think I proved that in chapter 1. But I think it's good to write here together. Okay, so I have some time to say something more. Okay. Any questions up here? Because today I give you several important theorems, and this theory will be applied later on For example, in chapter 5, right, we have a good foundation up to now about in the study of linear algebra. Okay. Yes, please.
我们上次有讲过那个矩阵维度不一样的话，它的代表就是如何？刚好让我有用到。
That inverse, okay. I think I can. The left inverse, no, I don't think so.
如果过瘾，那前面的这个就
Which one? Left inverse.
X等 C。
Yeah, has one. But not two, right?
是他说 as most one solution，代表说 X 等 C， 那 C。
The solution is unique at the most one, right? That's a solution, not the left inverse. A rectangular matrix may have a lot of left inverse, more than one.
那这种是 one solution。
That is for linear system. You talk about it, not the left inverse of a matrix. It's just. But I'm talking about if a matrix A has right, suppose if that, then AX, if you want to solve, right, if you want to solve this linear system, okay, if you want to solve this linear system is at most one solution. Because this linear system may be inconsistent, then no solution. Even you have this boundary, can't help you. But if this is consistent, then this boundary help you to say that the solution is unique. There is only one vector here, only one column vector satisfy this linear system. If the coefficient matrix A is left. I can show you how come. Well, you can think about A. Let me take an example. I can erase it. It's very easy to let me say 1, 1, 1. Okay. Now I can let 1, 1 here. So it's 2 times 1. So I want to find left inverse, right? Equal to an energy, that is 1 times 1. So that is equal to 1. Okay, and so it's 1, 1. Now equal to 1. Now you have to find it. So one way is 1, 0, right? Okay. The other solution, you can find many, right? You can have 2 and minus 1, right? So you have many left inverse. Any questions? Okay, so let me say something more. An invertible and has a matrix is also called non-singular. Right? So a non-singular matrix, square matrix, is same as talking about invertible square matrix. Just analogy. And a non-invertible m times n matrix is also called singular. So this is some terminology you have to know about that. Not still 10 minutes. So I can summarize. For an m times n matrix. So consider a square matrix. The following statements are equivalent. Means that they imply each other. Okay. So first of all, A is invertible. Okay. A is invertible for each B in the Rn, sorry, the linear system Ax equal to B base. Solution. It's a solution. The textbook gives you a stronger statement, say that it's a unique solution, but here I don't want uniqueness. Because once I have a solution, then it's invertible, then it should be unique. Why? Because that the kernel of A every column of A is a pivot. Every row of A is a pivot. Okay. So I make a remark here, and then that is only one. It's not necessary, right? Okay. But it's a consequence. So the statement here that everything implies each other. A is invertible, then you can say the range of A, the range of this, I mean the common space of A is Rn, or the kernel of A is just consists of the zero vector, or every column of A has a pivot when you get to the reduced row echelon, and every row of A has a pivot. So that is all the things. So sometimes people call this as invertible matrix theorem. maybe you can add more, right? So sometimes people want to add more. If you like, you can add, say, 6-1, A transpose. Okay, you like, right? The set. Because if A is a square matrix, of course the transpose A is also a square matrix. So A is invertible, then A transpose is also invertible. Can we have more? Let me see. Okay, yeah. I think you can write more here. So the rank of A is equal to n, because it's just a number of people you have. So it's n. A is row equivalent to the identity. So the row reduced echelon form of A is just identity. So it's a very, very good characteristic of any invertible m by n matrix. Because if you are start with an invertible m times n matrix, after you apply the Gauss-Jordan procedure, the n will be the identity matrix. Okay? So the reduced low echelon form of any invertible matrix is the identity matrix. Okay? So let's see. Can we have more? Another way to state 2 is that the column space of A is equal to Rn. Set. You use the column space, the concept. Can we have more? I have 4 minutes left. I'm searching for possible statement. I have no fixed textbook. I know. I'm just searching something and ask myself, and maybe I ask you. Maybe you can give me a hint, right? But up to now, you don't give me any hint. 3 minutes left. What can we say about it? Oh, one more. Okay? The set of all columns of A is linearly independent. Two minutes. One more. The set of all rows of A is linearly independent. This is my first time. I have more time than I expected. Whoa. The first time. No. 1 minute left. Can I get one more or two more? Yes, please. Oh, yeah. Okay. Okay. Good. Thank you. Thank you for your suggestion. That one is the rewritten form of concept. So the columns of A span are M. Yes. So the columns of A span are M. So that means that the column space of A, because the column space of A is just the span of all the columns. But you can say so, yeah. Almost done. Can we have one more in 30 seconds? Yes, please, please. I have two more. Okay. The linear transformation. I forgot the linear transformation. T represent x goes to ax, right? It's injected. Right? Injected means 1 to 1. 14. The linear transformation. T percent x goes to ax is suggested. Counter. So 15. The linear transformation. P x goes to back to ax, right? It's bijective. Means 1 to 1 and onto. Maybe this is I'm exhausted. So I stop here. So we have 15 statements. They are called invertible matrix theory, right? Whatever you want to include it, you can amend this at home. You'll be back. Okay, so I will give you the recommended exercise for chapter 3 and the coverage of midterm examination next Wednesday. Will be chapter 1 up to chapter 3. It's possible, and you can use one sheet, right, with both sides to write down everything you want to write. Formulas, theorems, anything. Okay.